getting rather hot in here, isn't it? Would be nice if we had some kind of permanent temperature display in here, yeah? Using a sensor, of course a chip, because we want to learn programming. IC editing, motherboard, computer and consoles? Well, there's more to the kit consoles than just consoles. We have LED small, medium and large, which needs 1, 2 or 3 consoles to build, and take care to rotate them correctly, because the LEDs will be not be rotated automatically correctly. It's a bit annoying. Blip, 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 plum, bladdle. Hey, wait, didn't I forget something? No, I didn't. Because this housing is just as good as the rear one, as long as we're not too keen on using the screws, which we're not by now, right? Here we can see all the housings that are available on the current network, which is currently only filtration. With or without chip, it would be listed here. Now for the program to run, once we have any, I need to turn the housing on, which in this case means the filtration unit. But what if I don't want this? There. Ah, now it's running, but it's not actually running. You can see here on the filtration unit documentation page in the Stationpedia F1, mode 1 is active, that's the default mode, but I set it to 0. So what does DB mean? I mean, we already know D0, D1, D2 and so forth for the screws. In this case we only have D1 and D0 and D1, because this thing only has 2 screws, which I'm not going to use anyway. But what is DB? Well, look here, in the case of the housing, we can say SDB setting and then a number, which is great for debugging. For example, aha, so DB is always just the device where the chip runs. Okay. So now we read the temperature of the room from this gas sensor. The gas sensor can read a lot of things. For example, well, the temperature. And also whether there's combustion going on, or the ratio of pollutant and all of that stuff. And what can the LED display show? Well, only numbers. It's again the value setting. Pretty common value. I wonder, will this work? It doesn't? Of course not, we have to use the right batch. It still doesn't? Well, it's an easy mistake to make and it can lead to really ugly outcomes, so take care what is selected here in the drop-down box. Ah. Well, this should read the temperature from the gas sensor and write it to the LED. Oh, and that's what we have, 314. What? 314? Well, it's Kelvin. 314, that is about what? That's about 45 degrees. Or 41, whatever. If you want this in Celsius, then we have to do some math. But don't worry, it's really, really easy. So first I'm saying load batch from any and all gas sensors. Oh, gas sensors? Gas sensors. The temperature, and since it's a batch command, I have to tell it what to do with those potential multiple values. I'm just saying sum them up because I don't care. It's only going to be 1. But will it only be 1? Let's make sure. There. And with this slight change, it will indeed only be this one gas sensor. And then this value in register R0, of which we have 16 from 0 to 15 inclusive, I go and write this value into the LED, but it's Kelvin. So how can we turn this into Celsius? We subtract. Now, like I said, the load command and the save command, they first want to know where to load and save something. I want to load into R0, or I want to write into screw 0, or I want to write batch into whatever device. The subtraction command and many other commands also want to first want to know where that result will go. And I will say the result shall go into this register. Which result, you ask? Well, we take register R0 and we subtract 273.15. Because 273.15 Kelvin is exactly 0 degrees Celsius, and the two also have the same scale. If you add 1 Kelvin, you have added 1 degree Celsius. It's exactly the same scale, but it is shifted. Kelvin starts at absolute 0 and Celsius starts at where water freezes. And so by subtracting from the Kelvin value this value, and the result goes here, we will now have Celsius. But only one time. Oh, it's changing, isn't it? Much better. Actually, don't forget you need to yield. I mean, you don't really need to, but you should. Control where the program will force the pausing of your program. Export. And that's what we get. Temperature constantly changing. Isn't it changing a bit unpleasantly? I mean, this jumping around back here of these decimal places, no one needs that. It doesn't help us. It is just irritating. Well, this should help. First, I multiply the value to shift a few of the decimal places into the integer realm, to the left of the decimal point. Then I say round, so cut everything off right of the decimal place, but with rounding, not just cutting off. And then divide again by 1000. This should help. So this is what we have right now. And after exporting, now this is useful. Yep, I dig. But it's still getting too warm in here. Well, we do already have a cooling solution. This here. Just an active vent that pumps from the station through a pipe that has pipe radiators, so there's much stronger convection, or in this case radiation connection going on with the outer world. And then we pump in again with another active vent. The problem is it's not automated yet, so let's do that. We will be controlling two devices of identical type, and therefore either we put them on the screws, which I have left behind me. I don't want to be dependent on that stuff. So we will just use the batch naming trick. That's it. There, now we have defined the vent and the two names. We have defined the gas sensor with one name. We have told the filtration not to run really, and we have our main loop with yield. We're loading from the gas sensor the temperature and we're turning it to Celsius. Let's take a little detour. You don't know the very important alias statement yet. With this I can say I give a register a name, and henceforth I can address it by still the register of course, but also I can use this name. Why would I do this? Because sometimes a value is one that you want to keep around for the entire main loop. Not just a temporary value like I did here in this situation, but I want to keep the temperature around. So with this kind of global value, it is easy for me to just digest it down here in a subroutine. I could have done this differently, of course. I could have said, move my Celsius temperature into whatever register I want to use in my subroutine down here, and then here I would have used that as an argument. I would have just used my R5 or whichever one I had chosen. But temperature I think is important enough to just keep around globally, so I don't use the argument concept by writing it decidedly into a certain register, but down here I will just pluck from the tree of global values and say multiply the temperature in Celsius that we have with 1000, write the result into my temporary value here, R0, round, divide, you have already seen that, and then write it back to the LED display. But why am I using R15? Well, if I use a temporary value, I will just use R0, R1, R2 and so forth. And my kind of permanent values, I will use R15, R14 and so forth. R15 is the highest one there is. Because then we have two worlds that will hopefully not collide. But anyway, for a moment let's change the temp variable, because I want to show you something. SGT. In case I didn't explain this yet, this produces a logic statement. I can say write into my register a logic statement of 0 or 1, and what I'm trying to derive is whether the temperature is greater than 45.1. Here we can see the temperature is not yet there. What temperature do we have then? Great. Too much rounding going on here, huh? Anyway, it's 45.1. Let's say 45.001, just to stick with the decimals, and And now we have 1. Aha. So the temperature is slightly higher than that. This is what we can use now. I can write into, let's say, register R0, whether the temperature is greater than 45. And now I can tell my 2 vents to, well, one sucks out of the room and one pumps into the room. And here I can tell them to just be on, according to what the logic statement is. So if the temperature is greater than 45, which will then be written into R0, then here we will have a 0 or a 1. So if it's greater than 45, then both vents will be on. Will this cool down the station, is the question. Oh, they're not reacting? What's happening? It's always good for debugging to try to operate them manually. You can see they are being addressed. They are being overwritten by the logic. So the logic has decided that things shall not happen. Why? Well, the temperature is for whatever reason falling. I don't quite get why. Maybe there's some non-insulated stuff up here, for example, which bleeds thermal energy into the outer atmosphere. That might well just be the case. When the sun is back, I guess we're gonna be glad that we have cooling. But anyway, let's use this threshold then. Ah, so something happening? Yeah, it's cooling down. Why is it not stopping? Because the temperature that we're measuring here is being measured here. The sensor is here. We just saw the cooling in action. It works, but there are some problems with it. First of all, look at the pipe. Minus 15 degrees? What's happening? Well, what's happening is that it has not been evacuated. The vents just turned on and then they turned off. There are 4 megapascals in there. It's completely out of control. This is not how you set this thing up, man. So let's turn off the filtration and pump the pipe empty.
Waste tank caution.
If we want the computer to do this for us, this emptying of the pipe, we need a pipe analyzer. It will tell us what's in the pipe when it's turned on. So let's make sure that the computer will turn this thing on in the way that a human cannot interfere with. Because else the human might turn this thing off and then we read the value and then the computer turns it on and then we ultimately read 0. And I don't know, in this scenario it might be harmless, but ultimately let's be in control of what's happening, okay? Now nothing can go wrong. So let's just read the pressure that the pipe analyzer tells us and turn it into a logic statement. If the pressure in R0 is greater than 0, which we can also write like this, then we want a 1. The 1 I will write into the same register because I don't need the old value anymore. And then I will just say pump in. So whenever there's pressure in the pipe, that vent shall be on, period. Let's hope the demonstration works out. So I will turn this one on. Has been turned on or turned off instantly by the chip, and the other one kicked in. See, they would both have turned on originally a minute ago with the old version of the source code if there would be if it would be too warm in here. But now this one, only this one does this. When I turn it on, there's some pressure in here, and this one turns on because there's pressure in there. And so now we have a cooling solution. Let's set a target temperature of 35 degrees. Let's work ourselves down. So if it's greater than 35, then the logic statement will be 1, and so there will be cooling. But let's check that the pressure of the pipe, 3 megapascals, 4 megapascals, is rising. We are not in control of the pressure. Why it is like this, I don't know, but I certainly don't like it. It shouldn't keep increasing like this. Of course, the active vents, they have some pressure protection in there. They have some built-in protection, but that's not the way I want to play this. What's the temperature? 36, so we were already there, almost. So I want to use different approach. Here I'm saying if the station, if R0 degrees Celsius is greater than 35, then the station is too hot. So greater than 35, jump to station too hot. And then jump back to start, whatever is going to happen down here. And otherwise we will fall through, and then we are here in station not too hot. By the way, if you want to do multiple things with the chip, you can also say cooling done down here, and just here you can say jump to cooling done, or here you can say to jump to cooling done, and then deal with different topics, with different tasks. But here we will just have the cooling for simplicity's sake. Right, there needs to be the temperature, of course. That was wrong. And here I'm also loading the pressure as a global value, because we will need that in one or two places. Up here before the main loop we are already doing some device initialization. Turn off the filtration to passive, lock the pipe analyzer, turn it on, and I've also set the direction of the two vents. What we already know is that if the station is not too hot, then all we care about is to empty the pipe. We just want it empty and then we are idle. So pipe pressure, if it is greater than 0, then a 1 will be in here, and the vent in will therefore be on, and then we jump back to start. That is all that we want to do in this case. Actually, no, not quite. The vent out shall be off. In case the station is too hot, we want to pump out the station air with vent out. We only want to do that as long as the pipe pressure is less than 2 kilopascals, no, 2000 kilopascals, which is 2 megapascals. So if the pressure is lower than that, pump out the station air into the pipe. And if the pipe pressure is greater than 1 megapascal, then the vent in, which sucks the pipe empty, shall be on. So there will always be a pressure of 1 to 2 megapascals, plus a little bit more or a little bit less even, because of some overshooting. But this makes sure that we have some good amount of gas in there, which will be effective cooling. It will not become too much, it will not become too little, and once the station temperature is fine, we will just suck the pipe empty. Let's see what that does. Why is this pumping still? Must be a mistake. Okay, now it's off. What I did is I just changed the threshold of the temperature. It was at 35, and as you can see, we have 35. Now I set it to 40, so it is not kicking in. It's not saying station too hot. So the problem must have been in the station too hot part. Now we're only executing this, and everything is happening as we wanted. So what's wrong down here? That's what's wrong. I want to check if the pipe pressure is less than 2000 or greater than 1000. I don't want to check if 1000 is less than pipe pressure or vice versa. That was just exactly wrong. You noticed the delay, huh? It's happening exactly as intended. It's a bit wild, but it gets the job done. And the station is cooling down nicely, except it's cooling down a bit much, isn't it? Okay, so the problem here was that I aimed for 35. Here is the cooling system, and maybe I should put the sensor just in a different place. How about here? Make sure you first copy the name. So that you can paste it again. So with this new placement, let's see what happens if you want to cool down to 30. I have no clue why the pumping in is so slow, really. I have used the very same setup in a different place. I don't know what the reason is. It doesn't matter, it's working. We can also, of course, make the pipe more extensive with more radiators to be even faster. It's normally not necessary. I mean, look here, the entire station is dropping by 1/10 of a degree so fast. And now it's still getting colder. Why? Because it's pumping in from the pipe. There was still gas in there, which was still cold or cooling down, so we're overshooting by a degree. We can just compensate by setting a different threshold. But now we have a cooling solution and it's entirely automatic. How much power does it need? 5 watts for the pipe analyzer, 10 watts for the filtration, as long as it's idle like it is right now. And of course about 200 watts while the thing is actually active. Which is, by the way, what the computer consumes also, 200 watts, so turn this thing off when you don't need it. And that's it. That's how you can make a little cooling solution that will serve you well. Goodbye for today.